Hello and good afternoon, everyone. We will wait. Things will start. So, welcome to another session of Asset Colloquium here. We are privileged to have a very renowned researcher, Dr. G. Rajalakshmi, from here from TFR Hyderabad, to give us an Asset Colloquium on atomic sensors, harnessing atom light interactions of precision magnetic field and detection. Rajalakshmi ji, as she is known as Raji with her colleagues and friends, has her prime interest in developing experiment techniques to probing fundamental physics with laser beams and things. She has built experiments for precision measurement of gravity and other fundamental interaction, employing torsion balances, laser-cooled atoms, and optical interferometers. She finished a PhD from Indian Institute of Astrophysics, and she is currently working in Hyderabad, TFR campus, and working on experiments on spectroscopy of low-temperature atoms, gravitational wave detection using LIGO interferometer, and more recently, nuclear magnetic resonance. So he's currently working on interaction of light with atoms and materials for applications in magnetometry and spin photometrics. I request Dr.
Thank you. Hi, everyone. I think I didn't specifically mention it in the intro I gave him, but of course, I have been part of TIFR for a long time. So that's why after IIO, there is nothing else mentioned because everything was TIFR predominantly. So yeah, it's nice to be here talking about some things which I've been doing in the last 5 to 6 years now. So this is developing atomic sensors for various applications. So before I get into the whole thing, I'll just to tell you the various things that we do in our lab. Main theme being quantum sensing and using light for sensing various things. So two main branches. One is to do optical sensing of things, of properties of 2D materials, again using the polarization of light. So we send in we use what is called a spin Hall effect of light, which is basically separating the two polarization states of light, which is done because of 2D materials. We use that to decipher the properties of very atomically thin layers of materials. I won't be talking about that today. But the other thing which we do is to look at atomic vapors and see how we can use the atomic vapors which are spins for detecting magnetic fields and other things. So that is what we will talk about today, mostly what is called as magneto-optical rotation. We also use the magneto-electric effect, but that I won't talk about today. Mostly I'll be talking about this part today. Before we forget about things, of course, all of that which we do is done in collaboration with a whole lot of people. I mean, these are the people from TIFR who work with Singh, and these are the people with a lot of engineering support from the workshop and other places. And we two collaborators from outside. Funding is largely DAE, and also I had a grant from SCRB and DRDO projects, which are mostly funded the research. But the work I'm presenting today was predominantly part of the thesis work of George Kurian, and some of it was also done by a postdoc here, Sushri. So let's get to see, what do I mean by atomic sensors? So atoms are sensors, of course, but when I say atomic sensors here specifically, it is basically the spin system. And the spin system I'm talking about are the valence electrons of atoms. So it is the electrons in the atoms which are going to be the sensors. And what am I sensing? Basically, multiple things can be done with them. You can do magnetometry and you can do gyroscopy. So one of the simplest thing one can do is what is called as nonlinear optical rotation, with which we can do both AC and DC magnetometry, and we can do RF magnetometry. And another interesting thing is what is called as co-magnetometers, which are interesting objects not only for gyroscope but for other applications. I will briefly touch upon them, but most of the talk will be in understanding how these things work and how one can make these atomic nonlinear optical rotation based magnetometers very good sensors. So we'll basically try to understand how these things operate today. So before we get into that, why are we even talking about sensing magnetic fields? Haven't they been going around for a long time now, and it's not something new? So what's so special about what we are trying to do today? And why are we trying to do things with atomic magnetometers? If you look at the current status of various kinds of magnetic sensors which are around today, I mean, there are various Hall effect sensors, magnetoresistance sensors. There are various kinds of sensors which are available in the market. And they can be classified by two things. One is sensitivity, which tells you what is the lowest field they can measure. And other is the size of the object, which can tell you what is the spatial resolution with which they can measure the field. So if you look at it, so if you go lower means better, more smaller fields it can measure. Similarly, small in this direction, if you go smaller means you can measure with better spatial resolution. So if you look at it, the most spatially resolved thing is what is called as an NV center magnetometer, which is based on, again, a spin, electron spin sitting in NV centers, but they are bad in terms of sensitivity. The most sensitive devices today are two things. If you look at it, this blue thing, this yellow, and this orange. These are squids, SIRF, which is the magnetometer, co-magnetometer I just mentioned to you about, and AVC, which are basically atomic vapor-based magnetometers. These three are the most sensitive things available today. So the idea is, since these are the most sensitive, we should be able to use them and try to see if we can also do things with them and see if we can improve their sensitivity even better, or can we make them smaller and push it that way. So the idea is to improve these guys. And so we are basically working with this atomic vapor cell based magnetometers. How do they work? Very simple. We will go into detail as to how it works. The basic principle is almost very, very simple. You come with a polarized light which is linearly polarized, which means it is electric field is oscillating in one direction. You send it through a gaseous medium in the presence of magnetic field. When it comes out, the polarization direction is rotated. Now, one just has to simply go and measure how much is this rotation, and then you will know what is the magnetic field. So if I plot the magnetic field as a function of the rotation as a function of magnetic field, it has this kind of a dispersive shape. But within this linear regime, you can see that if I measure the rotation, I can always go and find out what is the magnetic field. So now the problem of measuring magnetic field is a problem of measuring this rotation. So two things. I have to somehow make sure that for small magnetic field changes, I get large rotation. This line has to be steep. And second thing is, I need to be able to measure the rotation very well. So these two things are the important things to do. First, we will try to find out how we can make this slope very steep. So that is what we will find out how the slope even comes about to begin with. So how does this even happen? Sorry to put the experts, but forgive my thing. So when I said atoms and spins, of course, this is not one shouldn't be projecting this, but this is the picture which everybody understands. So when I talk of an atom, everybody will know that there is a nucleus and then there are electrons in orbits. So when I take it, and then when it goes from one orbit to another, it emits photons. That part everybody is kind of familiar with. But when these are in orbits, what these numbers are basically its angular momentum. These numbers correspond to their orbital angular momentum of the electron sitting in the thing. Just like, this is not the picture for the atom, but assuming this is the picture, it is exactly like something going around having an angular momentum. So that is what it is. This is called as orbital angular momentum. That is straightforward, since electrons are revolving, they have them. And these 1, 2, 3 are labeled as SPD. That is a label which somebody decided to give. That's what it is. But now the electrons don't only have this, they also have something called as a spin, which is intrinsic to them. So once you add the spin of the electron, which is the spin angular momentum of the electron, to the orbital angular momentum, you end up with something called as fine structure in this energy level. Each of these energy levels just changes. This S is basically, this S orbit actually has angular momentum 0, so that doesn't change. But these guys, angular momentum, it has some angular momentum. So when you add the spin to it, either the spin can get added or subtracted. So you get two levels like that. So now this nucleus also has a spin. Now I added the electron and added the electron spin to its angular momentum. Now I have to add the nucleus spin also to it. Only then I will get what is the total spin of the system. When I do that, this causes the energy level to split further. So when I add the nucleus spin to it, then you get some new number called F. And that number splits these energies more. So we started with this simple picture. This simple picture gives you this energy level, but the actual picture, these are the energy levels. So now the light transmission and absorption and emission will happen corresponding to these energy levels. And these energy levels are the ones which have a spin. And because they have a spin, these are like magnets. And because these are like magnets, they will respond to external magnetic fields. So it is the spin and these energy levels which actually respond to external magnetic fields. So now we need to do two things. I will just simplify this whole thing, and let's say I have only one light. I mean, for all this to happen, atoms have been, when I put light, atom has to go from one energy, from some level here to electron has to go from some level here to here. Let's take one ground state level, which for simplicity, I'm putting this number as 1. And the excited state has some number F equal to 0. When when this is 1, in the presence of magnetic field, what happens? This actually has 3 levels, which are corresponding to the magnetic field. Plus 1 has -1, 0, and +1. These 3 values are there. In the absence of magnetic field, these energy levels are degenerate. But the moment we put a magnetic field, the -1 energy level goes down and the +1 energy level goes up. Now, if I come in with light, and there is another special thing, light also carries angular momentum or spin. It also carries orbital angular momentum, but we are not talking about that kind of lights. We are talking about light which only has a spin angular momentum. And the spin angular momentum of light is +1 or -1. And +1 or -1 is basically called as sigma plus or sigma minus. And this is the circular polarization of light. So if I come up with a circularly polarized light, it has a sigma plus, and the angular momentum conservation means I can only do a transition delta MF, which is +1, because this spin has to get conserved. Same thing, if I come up with sigma minus, I can only do this. So this kind of already tells you that I can come up with the light and choose to excite only a special kind of transition. And also, not all transitions are possible, I can choose what I want to excite and what I don't want to excite. That is one thing. And now, if you come up with linearly polarized light, which is actually a combination of both sigma plus and sigma minus, any linearly polarized light can be kind of thought of as equal proportion of sigma plus and sigma minus light. If I come with that, and if I have a light which is exactly resonant with this transition, or the energy of the light is equal to the energy of this transition, in the absence of magnetic field, everything will get absorbed. Moment I put the magnetic field, it will no longer get absorbed, or if I tune it to one transition, it will not get tuned to the other transition. So just if I initially had a thing which was tuned to this transition, let's say, and now I put the magnetic field, now if I come up with linearly polarized light, now it won't absorb the sigma plus and sigma minus equally, which means something will happen to the light. I send in linearly polarized light, one of them will get more absorbed, other will get less absorbed. So when it comes out and I add them together, it will no longer be linear. Something will happen to it. That is the rotation. So the idea is, this is what it happens. But now the idea is, how do I create this? How do I make sure that more of one and the less of the other get absorbed? So that is what is called as optical pumping. So how does one do this? So you need to create a difference. So all of that I was talking about was a single atom, but now I don't have a single atom. I have a bunch of atoms. So I have to make sure that in that population of atoms, I have to somehow create a situation so that one of the levels has more absorption probability and the other has less absorption probability. That is done by what is called as optical pumping. So simplistic picture, let's say I have 2 ground states like we had before. Under normal conditions, thermal equilibrium, both the atoms will be equally probable to found in both states. So inversely, one can say both the energy levels will be equally populated. Now, if I put in a light which is resonant only with one transition, then atoms will get absorbed from here and go to this excited state. When they come down, they can come down to both. But whatever comes down here will get excited again. So if you keep repeating this process for a while, eventually this state will have less atoms and this state will have more atoms. Now I've created this population difference. This is also the kind of the population inversion which sometimes happens in lasers, but that is not what it is here. So basically what we are saying is now the 2 ground states which are supposed to be equally populated, now they are not equally populated now because we have created this using the light. So that is called as optical pumping. Now these 2 states have unequal absorptions. That is what I wanted. The idea is I need to create this. So I know I want to use a particular atom and I need to create this. So I've already chosen my atom, which is rubidium, and I know what light to use. So now I have to find out how exactly do I do this? Under what conditions will this happen? Of course, I can go and do the experiment, but before I go do the experiment, one would like to go and find out what is the optimal conditions to go do the experiment. Otherwise, I'll be blindly searching the parameter space. So what do? We set up the problem in a theoretical way. You write down the Hamiltonian, which is basically tells you how the system interacts with the world. So there are mainly three things here. So the atomic system, which is the electron and the nucleus, that is the thing. And then I gave the external magnetic field that interacts through that F, which I told you before. And then there is the light, which has both electric and magnetic field. But of course, we will only look at the electric field because the magnetic field is much, much weaker. So you put the electric field of light as well. And these are the only simplest thing which we need to put in. And this is the kind of external force which is every atom is seeing. This is the force which all the other atoms which are seeing inside, force or the potential, whatever, whichever way. The Hamiltonian is the systems which every atom is seeing this Hamiltonian. Now I need to evolve the whole bunch of atoms in this Hamiltonian and find out what happens. So one uses what is called as optical block equation. And these are called density matrices, which decide the property of not one atom, but a bunch of ensemble of atoms. And one goes around solving this equation by putting in not just the Hamiltonian, which is simplest thing. Now like I said, when I put the atom in the excited state, it will also come down. So there is a rate at which it comes down. So this is called as, and then after we create the population also, it won't stay like that. When two atoms collide, they will lose this population. So all of that relaxation mechanisms are encoded into these things. So you kind of solve this equation in a steady state and then try to find out what is the population at each in various energy level. You can do that and plot that. And I will tell you what this is in a minute. So this tells me what is the population. When there is very little amount of light and there is no magnetic field, as we expect, all the populations are equally distributed. This tells me what is the population, but I want one more thing. I want all these spins to get aligned to my external magnetic field. All these spins, as I told you in the beginning, are magnets. I want them to get aligned in the external magnetic field. This picture doesn't tell me what is the direction of these spins. To see that, it tells me the direction of these spins only in the space of the interactions, which is not useful for me. I need to know what is the direction of these spins in the lab frame where I am sitting. For that, we draw these probability surface. This is called as the atomic probability density. Sorry. So this is the angular momentum probability surface. So for simplicity, I have decided that my field is along BZ. So Z direction is where my field is. That is also the direction of my, that is also the direction in which the light beam is going. And my electric field is my light is polarized in the X direction. So my light is in this direction. My beam is going in this direction. And now I want to find out what is the direction in which the atom spin is pointing. So for that, we draw this. What is that? At every direction, let's say I draw a vector. The length of that vector tells me how many atoms are there with their spins pointing in that direction. So at every direction, I keep drawing this arrow. And then I connect the surface. Okay. If I do that, I get that. So when everything is equal, I get a sphere because the thing is basically equally distributed all over the place. So if it's a sphere, which effectively tells me that my atom's spin is pointing every which way. It can be anywhere. It is not doing anything. It is just random. So let's say I put some light now. When I put some high power light, which is what I said, when we put light, I can create this population difference. Now I put linearly polarized light. So both of these two things which M up with plus and minus, both can get more populated. So now we see the population in these two states is much higher than the population in the intermediate states. Correspondingly, if you try to plot the vector, what you see is along the direction in which the polarization is there are no spins. All the spins are oriented now in the plane perpendicular, in the YZ plane. The probability of finding the spins in the YZ plane is much larger. This is called as what we have done, we have gone and aligned the atoms. We have gone and aligned all the spins of the atoms in one plane. That's what the light did. Now I go and add magnetic field also to it. All of the populations went up. So what happened? The energy levels are no longer degenerate, and all the populations landed up in one place. Correspondingly, if I look at the spins, now most of the spins are now in the Z direction. So what I have done, I have also aligned all my atomic spins in the direction of the magnetic field. So the light and has helped us to go and align the atoms in the direction of the magnetic field. In the absence of light, they will align, but not so efficiently. The light plus the magnetic field means all of them have now aligned themselves very nicely in the magnetic field. Now, when this has happened, if I go and propagate the beam of light through this atomic system, which is all the spins have gotten aligned in one direction, then what will happen? That is what will create this rotation. So this, when I send a polarized beam of light through such a system, when it comes out, it will come out rotated. I can do this propagation also and then try to find out how much is this rotation. This standard thing about using you just try to find the amount of population in that, you just find the electric, how the electric field of light is affected by this population that you had by using this thing, and then you just propagate the whole thing using Maxwell equations, and you will get this. So I can go and do this and actually plot it as a function of magnetic field and as a function of this detuning means how far is the laser frequency from the atomic transition. So I change the laser frequency and I change the magnetic field and then find out how much is the optical rotation. So as you can see, it keeps changing, but for a certain rotation, there's a large change in the magnetic with magnetic field. What I need is with the magnetic field, some change should happen. There are certain detuning where nothing happens, and then there is some change keeps happening. And we had that initially. I showed that curve. No, the same curve is what you see here. But now I know at what detuning I get the maximum amount of rotation. So I know where to go and put my laser. Similarly, we also do the same thing by changing the intensity of light. One would think that if you keep increasing the intensity of light, I should get better and better. But simulation already shows us that is not particularly the case. Yes, it happens. Up to some point, it keeps increasing with intensity, but beyond that point, it actually drops. So keeping the intensity much larger than that is useless. So I know one knows what is the intensity. It should be of the order of few milliwatt, and I know what the laser detuning should be. So now you go and do the experiment. So the experiment itself is not very complicated. You take the laser beam, you take a small portion of the light to go and actually measure its wavelength and make sure where you are with respect to the atomic transition. And then you send the rest of the beam through a linear polarizer to make sure that the light is now polarized vertically. And then it goes through the atomic vapor. And on the other side, you have what is called as the Wollaston prism. Now, this part is what we need to do well so that we can measure the change in the angular rotation very well. So what does a Wollaston prism do? It basically separates the two orthogonal components of polarization. So if I come up with exactly vertical, I will have intensity only in one place. If I come up with exactly horizontal polarization, I will have light only in one. So initially, you make sure that your polarization is at 45 degrees. So both of these are equal intensity. And if you look at the different signal, it is 0. So in the absence of magnetic field, that is the state. Moment you put the magnetic field, because of the rotation, the intensity of one arm will increase while the other will decrease. So you just measure this difference and normalize it with the total intensity. That will tell you how much is the rotation. And since we are looking at very, very tiny angles of rotation, it is pretty much linear with the rotation. If it was much larger angle, it actually is a trigonometric relationship. But we are talking about very, very tiny rotations in the milliradian kind of energy. So all you have to do is so one can calibrate how much rotation corresponds to what difference in this thing using a standard wave plate or something. I can rotate the polarization by known amounts using some device called as a wave plate and already calibrate how much voltage difference corresponds to how much angle. And then I can just change the magnetic field and plot magnetic field versus optical rotation. Yes, in this case, it's a single beam configuration where the pumping and probing are done by the same beam. What we find out is that in this simulation itself was done for the single beam configuration only. So what we find is that for the single beam configuration, there is an optimum position at which you put the laser, which is not exactly the resonance, and that is where, in that position, you get the maximum rotation. So that is what we see here as well. So here, this is the absorption profile of the atomic system. And we just put the laser light at various positions within the atomic system. Of course, this is the position where the maximum absorption happens. But the position where the maximum rotation happens is actually here, slightly off. So what we see is that if you keep changing that, you get these curves of different rotation. And we find that this position is at some position here is where slightly off is where the maximum rotation comes. So then we can go ahead and fix that position of the laser there and then change the intensity. Here again, we go from very tiny laser powers of 250 microwatt to about 8 milliwatt. Initially, of course, it keeps increasing with power up to about 2 milliwatt. And beyond that, it actually starts to decrease again with power. So we know that we have to apply some 2 to 3 milliwatt of power and keep the laser frequency at this position, then we will get good rotation. So that is the thing. So in that position, if you go and do the experiment, what we also see is that now instead of applying how do we do all this? For doing all this, we actually have, there is this coil which is drawn there, which is basically a solenoid coil into which you apply current, known amounts of currents. It's already calibrated coil. So I know what current corresponds to what magnetic field. So that's how I figure out, calibrate the system by finding out what is the magnetic field and versus rotation. Of course, then when I just measure the rotation, unknown magnetic field, I can find out. So the idea is instead of applying a DC field, if I apply AC field and I keep changing the frequency of the field, I can find out what is the frequency response of my detector. And that shows us that we have a bandwidth of about 24 kilohertz. So we are able to, so the sense, and then the lowest signal, the noise floor, if I see when there is no signal at all, it is about 1 picotesla or below. So if the detector noise is at the level of about 1 picotesla and my detector bandwidth is about 24.5 kilohertz. So I can actually measure changes as small as a picotesla, and this is what it is. And what exactly decides our noise floor? Is it electronics or whatever it is? To see that, what we do is now, instead of looking at the rotation, I just look at the voltage signal coming from the detector. And if I plot that in the absence of any light, if I just cover the detector and then take, this is the noise flow. So that is my electronic noise flow, basically from pickups or whatever, the electronic noise flow. But the light itself does that. So this shape also tells us that the response of the detector is not uniform across various frequencies. So the detector, even though it's supposed to be a broadband detector with a bandwidth of about 100 megahertz, and I'm only in the kilohertz regime, it has a slight change in its response. I mean, this is very tiny. This is 1 microvolt to 2 microvolt. So the actual change is much, very tiny. But this shape is there, and that kind of also shows up as a funny kind of kink here. But it also tells me that this is basically, with the light, the noise floor went up. So my noise is basically decided by the photon shot noise, by the fluctuations in my light source. Some of it could be intensity fluctuation, but we know because we have locked the intensity laser that it is not the intensity fluctuation, but it is basically intrinsic fluctuation, the photon short noise limit, which is what is deciding our sensitivity at this point of time. So another interesting thing about our detector is that, of course, another thing which I forgot to mention here is, while doing all this experiment, there is this S, which is basically a shield. We put the whole thing inside a magnetically shielded region, so that the only field that the atoms are seeing is what is generated by the solenoid and not any environmental field. So most of these experiments were done like that. That is why we could go all the way down to picotesla and see stuff, because ambient fields could be much larger than that. But then to test the sensor, we also put it in an unshielded environment. So in the shielded environment, we got the slope of like this. In the unshielded environment, also our sensor slope is bad compared to this, but it's only off by a factor of 2 or so. It's only half of this. So not only when we see picotesla, we can see the picoteslas even in ambient environment, in earth field environment or ambient environment, and our range of operation is of the order of microtesla. So these are the main. At this point of time, yes, study DC field also we have done some experiment, but whatever I am showing here right now is for this is for a 1 kilohertz. Yes, 1 by F will take over, but yeah, at this point of time, this is for up to about 500 hertz, this works. That we have seen. Yeah. So basically we have a single beam room temperature system which works about picotesla sensitivity, and it has a dynamic range of about 10 to the 6 because it can go up to about microtesla, and it has a bandwidth of about 25 to 30 kilohertz. Of course, again, the same repeated. Why, I don't know. Fine. The deal is we want to go lower. Some things we know that we should do, which we have not yet done so far, is we are operating the system at room temperature and we are using rubidium. Rubidium is a solid at room temperature, but its sublimation temperature is like 40 degrees. So even at room temperature, there is enough vapor. It is not very high. It's very tiny. It's like 10 minus 7 torr kind of pressure, but that gives us enough signal. If I heat it to 50 degrees, which is just above the sublimation point, the number density will go up a lot and my signal also will go up a lot. We have not done that. If we do that, we know that the signal will go up. And also we know that we are using 85 rubidium because that is what was naturally abundant source. But if you use an enriched rubidium source with 87, the transition probabilities are different. So that it actually, for the same amount of intensity, it gives much more rotation. So that is another thing which we can try. Some of these things, if we try, we hope that we should be able to go down in sensitivity a little bit more. So all of this, as I said, this works for DC, as AC, but we also went ahead and made a system with the DRDO people. This is now we are trying to do, hi. This particular system, as I said, it goes up to 500. And this system which we are trying to build here, the DC field also, we are able to go up to about a picotesla. So here we try to, similar system is what we have built. This is slightly modified system. I mean, when I say DC field, but here what we are doing is, we are using some modulation techniques. Meaning the magnetic field itself is not modulated. Magnetic field is what we are measuring. But I can go on add a frequency to the light. I can go and modulate the intensity of light at a certain frequency. So when I do that modulation and demodulate the light, so I am detecting at 1 kilohertz, so my 1/f noise is gone, but my field itself is DC. When I do that, we still manage to get about a picotesla sensitivity for a device like this. This is now made into some handheld kind of a device. This is an optical table with about 1 inch gap of each. So this is like about a 10 centimeter, this thing, and it has the electronics and all is kind of, the detectors are stuck on one side with the electronics and the laser comes as a fiber in the other end. So the whole thing is like a handheld probe, while the control electronics sits in a box somewhere. Right now it is not in a box, but it's on the table. But yeah, it's getting converted into something like that. But the idea is this has been done now, the handheld probe and the testing in ambient condition is the next thing that we are planning in the next coming months. This project, basically idea is to be able to measure geomagnetic fields and see what happens. Of course, this is with DRDO and their interest is to look for mines and submarines and things like that, which they will eventually do with some help from us, I suppose. But in addition to this, what is interesting is these kinds of sensors, of course, this is still a little big, but smaller versions of these sensors which are commercially available are also used for measuring EEG and MEG, magnetoencephalograms. Basically, electric fields and magnetic fields coming out from our brain and from our heart. These are all measured by these kinds of sensors, and they are useful for those kinds of things. So it's a nice idea to be able to develop these sensors into devices so that they can be used for various applications. Yes, actually these are at the picotesla level. Some of them are actually even larger, nanotesla levels, but yeah, heart and these things are at the picotesla level. We are not overcoming, we are looking at picotesla changes over and above the Earth's field. Earth field is still there. We can't do much about it. Huh? Yes, so that this is,
how do I make out that it's not some fluctuation in
it's not very straightforward. You have to, of course, you have to do various techniques. Like typically, you have multiple sensors, and then try to find out the common modes saying things, and you try to send some signal and then see what you get back. So we have to do some amount of things to get rid of it. And more than another thing, what was I going? So this, for example, so this itself is measured in the presence of Earth's field. So of course, this thing is shifted from zero. The zero is not at zero. The whole thing is shifted here and it came there, but the slope is still available for me to measure. The picotesla changes over and above this. The zero rotation is not happening at zero, but at something. So, yeah. So it is not, I mean, one detector alone by doing this is not very straightforward. Usually you will have to put in, typically what we try to do, for example, is put an accelerometer or something next to it. Then you know that if anything is moving and that is what gave the signal, that is not what I want. I want signal from something which is not there, but which is stationary or whatever, things like that. So those kinds of, it is not a, I mean, right now these devices are just being used. So a lot of things about it has to be learned while as we go along. So yeah, so that is needed. But these things are already being done with commercially available sensors. I mean, not in India, but in other places. They stick a bunch of these tiny sensors in a helmet around your head and measure the brain signals. And they also put it on and measure the electric field signals. Yeah, but yeah. So in that is exactly why I think what we are building will work better, because the sensors these people use are sensors which have bandwidth of about 100 hertz. And they are using those to measure these, because most commercial sensors work in a regime where they cannot work at high fields, because these measurements are again done inside shielded rooms. The patient is sitting in a room which is magnetically shielded. Of course, which is better than going and putting your head in that huge MRI magnet, but still, it's a quiet room you're sitting in, and then they do the measurement in those kinds of fields, and still they have 100 hertz bandwidth. So fast transients they cannot see. So that is why we thought that we should, I mean, our device, probably if we are able to reduce the size of our device without losing its sensitivity or the bandwidth, we could probably do better than what the commercial sensors are doing today. Okay, it is a little bit not, olden days submarines were easier to detect because they were made out of iron and stuff. So they will have magnetic field. These days people use non-magnetic materials and things like that. But it doesn't have to be submarine. What it can detect is if there is a complete difference in terrain. The presence, for example, there is only water and there is no water. In that, if there is a submarine, the volume of water there is gone. So that difference it will detect. This will be on the floor. It will be on the floating on the sea. It will be on a buoy. It will be on a buoy. In fact, some of these, these picotesla fields, if you have a sensitivity of a little bit better than picotesla, you don't even need to be on the sea. You can be on a drone. It can detect things which are, I mean, that is why you need picotesla, because these fields are much larger. We need this picotesla or femtotesla because we cannot go close to the device and measure. We are measuring from far away. Because we are measuring from far away, we need these things. We need that kind of sensitivity. Otherwise, of course, even what is available in Hall sensor will also measure them. But we need to be near it. It will, because that's why you need the DC sensitivity. That is why our system should have a DC sensitivity also very high. The first, there are two different, there are multiple kinds of magnetometers. I didn't explain all the magnetometers that we developed in the lab. I explained in detail one which is very special, only available in our lab, which is the bandwidth. The other one is available even commercially, the one which goes to DC, but that has a lower bandwidth. So what we have developed here is a DC detector. This is not a one which measures only AC. This is designed to measure DC. Huh? It can do AC up to kilohertz. That is the target aim. Unfortunately, we have not completely measured the bandwidth of this at this point of time, but yeah, at some point we will measure it and tell you. But we have looked at it respond up to about 4 to 5 kilohertz and it works. We have not gone beyond and seen it, but yeah, systematic study we have to do. And okay, we did all that. Of course, the whole purpose of our developing this, the original concentration of developing this broadband magnetometer was because we were not interested in going and measuring mines, but we were interested in looking at NMR signals, which are not that slowly varying. They are varying it at some rate, and we wanted our detector to be able to see those things. So based on that, we built an NMR system. Before I tell you about that, I'll just some 2-slide primer on what exactly NMR does. So in the standard NMR, people use very high magnetic fields for creating polarization, meaning I need to, now just like we went and aligned the electron spins in the atom, I need to align all the nuclear spins in one direction, and then only I can get some signal in a big NMR magnet. So that is why so that polarization depends on the magnetic field and the temperature. But so even in high field, they put it, and then also they get very tiny amount of polarization. So of course, if I'm saying that I'm going to do it at earth field or lower than that, one will get even lower polarization. So it looks a little odd, but that I'll come back to why we want to do that. And the signal is decided by so when you put a magnet in the field, it will start processing, and the precession frequency decides the signal. The signal is detected by putting a pickup coil, and the signal in the pickup coil depends on the rate, how fast the spin is rotating. So the Lama precession frequency has to be large. So having a large field helps in that as well. So standard pickup coil detection will also not work because in the low field, the frequencies will be less than a kilohertz, or so that also won't work. So we need other kinds of detection techniques. That's where we wanted to use the atomic magnetometers. Of course, and we need to create some polarization, at least of this order, and that we will do by doing something called pre-polarization. There are various ways of doing it. We do the traditional way of putting it in a magnet. So why do I do all that? When I do, normally when I do it in a high field, so these are the various interactions which happen in a sample, standard NMR sample. Strongest interaction is the interaction with the external field in the standard NMR, which is basically there are Zeeman interaction, chemical shift. This is the standard interaction which is used to do the standard chemical fingerprinting with NMR. These two interactions are both dependent on the field. So they are of the order of 10 to the 7 hertz per Tesla or 10 to the 2 hertz per Tesla, and the standard NMR magnets are of the order of 10 to 20 Tesla. The maximum highest field today is about 20 Tesla. So this can go all the way to gigahertz, and this will be something like that. So this will cross splitting. But most of the interaction between the nuclei, this is called the J coupling or the dipole-dipole coupling. J coupling is the through bond coupling, and dipole coupling is just free space coupling. These interactions are in this regime of this J coupling is in the few hundred hertz, and this is kilohertz. And the quadrupole, most of the NM spins are actually quadrupoles. These are in the kilohertz to megahertz regime. All of these will be completely suppressed in the high field because this 700 megahertz or 1 gigahertz or whatever that is will basically suppress all this. But if I go and do in the low field, so of course, if I write the total Hamiltonian of the system is all of these. In the high field, only these two terms dominate, but in the low field, this is almost gone and this guy dominates. The idea is to do experiments in this so that one can study these interactions in the absence or in the present, very tiny amounts of this interaction. So I want a detector which can work in this regime, kilohertz. That is the whole purpose of going and building that atomic magnetometer. So then we went and built this system. So what do we do here? So we have a pre-polarizing magnet. Sorry. Which is a homemade Hallback magnet, which gives a field of about 0.7 Tesla. So the sample is initially kept in that for about a few seconds, and then quickly pneumatically shuttled down to a region here, which is in the shielded environment. And then the atomic magnetometer is sitting inside that. And in there are multiple coils. There's one coil, which is two things, which is called as a guide coil, which is when the sample is moving down, we don't want the earth field to scramble the polarization created by this. So we apply a very mild field so that it guides the spins down in that field. That's called as a guide coil. But it is also the coil which can apply a field in the Z direction. And then we have Helmholtz coil to apply fields in the X and Y direction. So one can apply fields in all these directions. And the fields through all this current are controlled by some current circuits which we made ourselves. And all the timings are controlled by some Arduino microcontroller chip which we have made. All of this is controlled by a PC, of course. And then the signal from the magnetometer is given to an oscilloscope and then observed in the detector. So idea is to, so we use this, and now this whole thing becomes the NMR spectrometer. So this is how it looks in the lab. So the electronics are all sitting like this at this point of time. They will have to be boxed at some stage, but yeah. So this is the red thing is basically the magnet. There are, and then this shield, the detector is seen here. The sample is sitting here. The medium cell is sitting here, and you can see the photo detector outside. The light beam comes there. So what did we do with this? Of course, first of all, we have to demonstrate that this thing, whatever we have built is actually a spectrometer and it is detecting what it's supposed to detect. So the simplest thing to do is to put water and try to look at the proton signals from water, because everybody knows. So what did we do? So since we have this coil, I can apply known amount of fields while detecting. I can do a standard NMR-like experiment, but now with microtesla fields. So if I keep the BZ field on for some time, and then I apply, so the spins are now in this direction, Z, and then we switch off that field and switch on a field along the X direction for an amount of time which we know that is a time which corresponds to the 90-degree pulse, meaning it is the time it takes for the spin to go from there to there because of the Lama precession frequency. So you keep it on for that kind of time, which is called as a 90 pulse. When I say 90x pulse, a pulse applied for the amount of time equal to 90 degrees applied in the X direction. Here, when we say pulses, unlike in the NMR where they apply RF pulses, here it is just a DC pulse. It's just a current which is going through the coil for some time. So you apply that pulse, and then these things are here now, and then we again switch on this field. But now at varying strength, the strength of the BZ field during this detection, I can change because it's coming from the coil. So the Lama precession frequency, which is the atomic magnetometer will detect this signal. Now this thing will precess in the plane and the detector will detect this signal. So if you look at that signal, and I can do the Fourier transform of that and plot it. So depending on this field I have applied, the Lama precession frequency will shift, and that is what I see here. So if I change the frequency, the BZ field, Lama precession frequency changes. So I know that my detector is working as a NMR detector. And then we also tuned our electronics to be able to do the standard NMR experiments by applying a 180, what is called as a spin echo experiment, where you apply the field for some time and then apply a field in the orthogonal direction for the time, double the time of the 90 pulse, and do this so that the spin decoherence can be removed. These are standard spin echo experiments which are done in most. So we just built our experiment to be able to do all that. So basically what we can do is between this experiment and this experiment, this experiment will measure the T1 relaxation time, or the relaxation time, the time it takes for the system to build the magnetization. And this measures what is called as the T2 relaxation time, which is the relaxation because of interactions. So these kind of things can be measured. Of course, this is just the beginning of the thing. So idea is we can measure NMR signals with fields, bias fields in the range of nanotesla to microtesla. And the whole thing was just built in-house. So we can modify our experiment to do whatever it wants at any time of time.
What are you measuring?
I am measuring the magnetization from the sample using the atomic magnetometer. The atomic magnetometer measures the magnetization of the sample. So instead of the Lama precession frequency, I am directly measuring the magnetization. So if the magnetization is rotating, it will measure the projection in one direction. So
The next slide, if you go to 20, I didn't understand why you're getting two signals before we change the magnetic field.
Yes, these are two signals at two different magnetic fields. Yeah. I mean, we can also do phase cycling and all that. It's details, so that's okay. Yeah. So the thing is, in our setup, we can do field dependent NMR, which is not easy with a big magnet. And one can measure these kinds of things like T1, T2 relaxation as a function of field, which is very useful in certain applications in material science and in food science and things like that. So we want to explore those kind of possibilities. Another I didn't put it here, but another interesting thing that we can do because of this low field is, for example, if I want to measure something which is inside a metal casing, like battery or some other whatever thing which is in we cannot do it with a standard NMR machine because the RF will not penetrate that kind of a metal casing, and it will basically screw up the whole thing. The eddy currents will just mess up the whole thing. But since we are now operating at very, very low fields, one can do this. One can do in situ measurements on things like electrolysis and things like that can be done. That is another thing which we want to explore with this. Okay, beyond that, this is a little out there. What more can I do with this magnetometer? This is not what I am doing, but this is what people have been doing around the world. These same magnetometers can also be used for testing fundamental theories. Just 2-second primer. Basically, everybody knows that there is standard model and in which there are two main forces, electromagnetism and gravity are the macroscopic forces. There are other microscopic forces. And usually their mediators are some bosons, which are spin 1 boson photon for electromagnetic wave and spin 2 boson graviton for gravitational wave. The idea is the new theories predict that new macroscopic forces exist, which means there are new massive bosons. In some sense, these are the bosons which also are supposed to form the dark matter candidates. The idea is to see, can we detect them? If these things can give rise to two kinds of forces, spin independent forces, which will lead to modifications to gravity itself. And then there could be spin dependent forces, which will happen between polarized objects. So how can we use an atomic magnetometer for this? Especially for the spin dependent forces, because the spin dependent forces basically generate a pseudo magnetic field. And the alkali atom electrons will get affected by these pseudo forces. And one can this will appear as an anomalous signal in the magnetometer. So one can look for this signal and then put limits on the new forces, new massive objects and things like this. So basically these are parameterized. All these new interactions are simplistically parameterized by two things. One is some interaction strength, and then by the pseudo magnetic field that it generates, then it will look like a Zeeman-like interaction. And then people have done these experiments using slightly different form of what I just now explained. We only talked about having one alkali atom and the laser. So in addition to the alkali atom, you also put a noble gas atom. Why? Because the alkali atoms can be nicely polarized and aligned by the laser beam. Then when the alkali atoms interact with the noble gas atoms, there is Fermi contact interaction between these two, and the noble gas nuclei get polarized. So this kind of a mechanism, by keeping these two guys at a particular pressure and all that, what will happen is that using the light, you polarize the alkali rubidium. The rubidium will go and polarize the xenon, so that the xenon will also now get aligned with respect to the external magnetic field. Why do I want to go and polarize the nucleus and not just use the alkali atom? The electron polarization, electrons get polarized fast, but they also lose their polarization fast. The nuclei take time to get polarized, but they don't lose their polarization also fast. So if I keep that polarization alive like that, now if the whole thing rotates or something happens, the xenon will just follow the magnetic field wherever it goes. And because it is, then I will know whether, so this whole thing is called as this is what is used for gyroscopy. But now I can just monitor interesting thing is now I can monitor the nuclear polarization, which is again a spin which is right next to the rubidium. So the rubidium will get affected not only by the external field, it will also get affected by the xenon field. So when if the xenon, something happens to the xenon magnetization, that also the rubidium atom will see. So one can measure what is going on to the xenon using that. So that thing, okay. This kind of this whole thing operates in a very low field regime with a high density, which is called as a spin action relaxation free regime, which I will not worry about here. The idea is now use this xenon spin polarization for tracking the pseudomagnetic interaction. So people have done these experiments, and by just in this particular experiment, they actually put a material with varying spin and rotate it next to it, and then look for a synchronous change in the magnetometer. And the null experiment, the fact that they didn't see anything means they can put some limit on the anomalous fields. And similarly, people have done these experiments, and yeah, it's out there, of course. So to conclude, basically, what we have done, of course, is to build something which is about a sensitivity of picotesla and 25 kilohertz bandwidth. We have used this, of course, for making NMR experiments. The idea is we want to improve this further to go to lower and increase the range of frequencies we can measure and things like that. That's happening. We are also trying to make a device out of this thing, which is one thing. And we are trying to expand on the zero field NMR techniques further to see if we can actually use it for something in the real world. Thank you.
Thank you very much for this. Open for question. Request is just wait for the mic and then speak, so the audience on Zoom also can hear your question.
For these sensitive DC magnetic field instruments, what exactly are they used for in practice?
And these are the things which are right now, these are the instruments which are being used for all these measurements as well.
What I'm saying is that what are the applications of
the DC magnetometer, that is standard applications like any other magnetometer, but the defense people are, of course, want to use it for detecting mines, tunnels, and things like that, because those are very slowly varying things. It's almost DC. You just take something and walk around, and then it is at the speed at which I walk around, or something flies around. Those kinds of things, yeah.
So the detectors have to be sensitive because you are far away from the source of
yes,
magnetism.
yes. They have to, basically because of the distances.
Raji, question here. Among the applications that you listed, you also mentioned about food science. So what I was just intrigued. Yeah.
Basically, the simplest of things is, let's say I take packaged food. If I have to package it, I need to remove water. I need to make sure that I've actually removed the water content. So by measuring the relaxation rate, I can find out whether there is water in my sample, in my thing or not. It's simple. So various things. Another thing which I was reading a paper, and of course, I myself am not an expert here, but since I'm also trying to learn, so I'm reading a paper. One other place where people seem to be using it a lot is to find out how good the pork is. The softness of the pork depends on its amount of hydration. So very quality of food. The quality of food depends on how much water is there or not there. So you can measure that. That is the main thing. And they usually try to use tabletop NMR or big NMR machines, and it's complicated. Of course, this is much smaller, easier to deal with. Portable, much more easily to carry it, walk around. Yeah. Four sizes. Here, basically, again, the same thing. If in some solvent, you put these things. And yeah, so basically, the simplest thing is that. So let's say I'm exaggerating. If my porous medium has this kind of something, and I put some solvent, the water here will be very close to this surface and it will relax faster. Sensor is outside. I'm just doing NMR. That is okay. I think the sample is inside this coil. My light, this box here, I don't know if you can see it. That is the rubidium cell. So my rubidium cell, whatever, sits there and my sample comes close to it. Yeah, that is the whole point. The heterogeneous sample is fine. I'm only sensitive to this portion of the sample anyway. I don't see anything else because steel will fall off very rapidly. The idea is even in that region, what you are measuring is relaxation rate of the water. So depending on how much surface it is seeing, the relaxation rate will be different. So one can do a field dependent relaxation and then find out how this works. There are the standard Lorentzian theory which follows. Yeah.
Anybody else? Anybody on a Zoom room has any questions? Can please unmute yourself and speak. I think there is no more question at present, but of course, people can interact with her at the tea, which I will request everybody to come. I'll also appreciate the wonderful talk that she gave us and opened up our entire fantastic things. Hopefully, she will materialize it much better than that and come back again in a year and say that this is the realized one with the DRDO. Also very happy with it.